Okay, let's get started. I want to start by reviewing what we did last time. So we started the conversation about feedback control, and to be more specific, it's negative feedback control, where we compare the output of the system with the reference input, and we decide what the input to the system is going to be based on that comparison. So this is the typical block diagram of a closed loop system where our objective is to control the plant, G of S. And in order to achieve that, we need to sense the output of the system. That's why we have H of S as the sensor. H of S represents the dynamics of the sensor. And the goal of this feedback control system is for output of the system Y of S to always follow R of S as close as possible. That's the overall overarching objective. And the mechanism by which we try to achieve it is through this negative feedback. So we continuously compare the output of the system with this reference input and continuously feed this signal, which we call the error signal. The difference between the output and reference input is the definition of the error signal. This continuously enters the controller, and the controller in turn continuously adjusts the input to the actual system. H of S is also known as the open loop system, the system without a controller. And when we close the loop around our open loop system, this overall system is called a closed loop system. We talked about this general golden rule by which we can reduce this entire closed loop system to a single transfer function. This single transfer function, of course, like any other transfer function, has a numerator and a denominator. The numerator consists of all the blocks that would sit between the input of the system, which in this case is reference input, and the output of the system. This straight path in this case consists of f of s, c of s, and g of s. And you can see that the numerator of the resulting transfer function is made of multiplication of these three. Because we have a negative feedback, the denominator of the overall transfer function would have a 1 plus. And after plus, we have everything that is included in the feedback loop. So we start from the summation sign and end at the summation sign, and all the blocks will get multiplied by each other after the plus sign. That was one of the major concepts that we discussed. And the next thing was this tool that we call root locus. Root locus is a collection of location of closed loop poles, the poles of this closed loop system, as a single parameter changes. In this case, that single parameter is the controller gain k, but it doesn't have to be k. It can be other variables, and it's still that collection of closed loop poles is called a root locus. So if you recall, we looked at this example where we had a first order system as our plant, as our open loop system, and we closed the loop around this open loop system through this controller. We took the output, we compared it to R, created an error signal, which went to a constant. So our controller is the most simple controller possible. So we multiply the error by a constant, and that's how we calculate the input to the open loop system. We applied the rule that we just reviewed to find the transfer function between R and Y. And from there, we could find the pole, this only pole of this transfer function, by setting the denominator of the closed loop transfer function equal to 0. We found that that pole, that single pole, is located at minus b minus ka. Versus when we were only looking at the open loop had one pole and it was at a specific location. It was not changing. The pole of the open loop system was located at negative b. But for the closed loop, the pole is located at negative b minus ka, which means it changes, the location of pole changes as you change value of the controller gain k. And if you draw that fact that the location of pole changes with change of k, you arrive at your root locus. So this is the root locus for this system, which shows when k is equal to 0, the pole is located at negative b, and as k goes to larger positive numbers, the pole shifts to the left. And we looked at MATLAB, and I showed you that as k changes, the system becomes faster, which is expected. If a system has poles that move to the left, the system overall gets faster. We also did another part of this practice where we calculated steady state value of y, and we showed as k also changes, this is a steady state value of y in response to a unit step input. So as k changes, this y steady state gets closer and closer to 1. So that was the other calculation we did. Now, if you please open MATLAB. If you use MATLAB, the actual MATLAB software, not the web-based software that we have, you can click on your root locus, and at each click you can see the value of the gain and the associated performance of the system. So if you haven't opened MATLAB already, please go ahead and open it. I'll show you that feature as soon as you're ready. We also looked at this example where we talked about a cruise control system, which is a first order system. So we have the transfer function of the open loop as 1 over ms plus b, where m is mass of the system, b is the drag coefficient. And we wanted to look at the performance of the closed loop system when r, the reference input, the desired velocity of the car is 10 meters per second. And we wanted to achieve this 10 meters per second with a specific transition type response. So we wanted the rise time to not exceed 5 seconds. Rise time is the time that it takes for the response to go from 10% to 90%. So this initial change. And also we didn't want a steady state error to be more than 2%, and we didn't want overshoot to be less than to be more than 10%. So we wanted to keep overshoot less than that. So that requires maintaining a certain value of natural frequency, as you can see and we reviewed last time on this slide. So we need to maintain a certain value of natural frequency, and we need to exceed a certain value of damping ratio in order to achieve the desired value of rise time and the desired value of natural frequency. The desired value of overshoot, rather. So if you plug this overshoot that you can tolerate into this equation, the equation for zeta, so let's say your overshoot is 10%, which is 0.1. If you plug it into this formula, which is square root of natural log of 0.1 squared over pi squared plus natural log of 0.1 squared, you can see that your damping ratio has to be 0.6 and larger. So if damping ratio is 0.6 and larger, then the overshoot will stay less than 10%. Now, if you recall, when we were talking about standard second order systems, I showed you this graph. This graph shows you that as you move the poles from the imaginary axis towards the real axis, the damping ratio increases from 0 towards 1. So therefore, we know there exists a specific line associated with 0.6. So on this plot, so if you look at this plot, so if this is 0, there would be a specific point on this plot that would be associated with 0.6. So let's assume this is 0.6. So if this is 0.6, so if this is 0.6, zeta equals 0.6. There is also the symmetrical line here, also for zeta 0.6. So if you want a system that maintains an overshoot of 10% and less, this area, any area between the two lines is acceptable for locating your closed loop pole. In this case, it's one pole, but if you are dealing with a second order system, there are two poles. So that's a key idea when you're applying root locus. When you're applying root locus, you need to identify the area of complex plane that you want to locate your poles to that plane. So let me go back to our example. So we know by now that our zeta has to be more than 0.6. So the first thing we know based on maximum percentage overshoot. So we want maximum percentage overshoot to be less than 10%. From the formula, you get that zeta has to be at least 0.6. Now, this is 0.6 on the complex plane. So this is the line for 0.6 here, the symmetrical line here. So that means any place to the left of these lines, so everywhere here, is acceptable. Outside that, of course, the damping ratio is less. If you go to the right of those lines, the damping ratio is less, so you can't, that's not an acceptable region for the location of poles. So that was one of the requirements. The other requirement was for the rise time. And the formula for rise time is omega n has a relationship with rise time. So if you want your rise times to be 5 seconds and less, that means your natural frequency has to be 1.8 divided by 5 or more. And that number, so if you take 1.8 divided by 5, that number is 0.36 radians per second. So again, if you look at this area, this circle or this half circle is associated with natural frequency of omega and y, because if you recall the distance from the origin, so the distance from the origin to the pole was natural frequency. So if one of the two poles is here, this distance is natural frequency. This distance, equivalently, this distance is natural frequency. So you can come up with a circle of radius 0.36 and draw that circle. And if you want a rise time to be less than 5 seconds, you need to be to the left of this area. So if this is the semicircle, this is the acceptable area. Because if you're to the right of this, your natural frequency would be smaller than 0.36, and therefore you don't get the rise time that you expect. So if you now add, so you need to be to the left of this line, and you need to be to the left of this semicircle, that defines the area that is acceptable. Now I told you if you do root locus in MATLAB, so let me switch screen here. If you use the complete version of MATLAB, you would see, didn't switch. You would see that you can actually click on root locus, and as you move around, you can see the values. So let me see if I can get this guy to work. So what you need, so if you have MATLAB open, you need to define your system. So you need to define S as the transfer function variable. And then your transfer function for this system is 1 over ms plus b, where m is 1,000 and b is 50. So your g is 1 over 1,000 times s plus 50. So that's the open loop transfer function, g. And then if you type root locus, r locus of g, you get the plot. Nice. R locus of g. You get the plot. And the next command that you need to use is sgrid. So type sgrid, open parentheses, and the first item is your damping ratio. So 0.6 is, we decided that we want damping ratio of 0.6 and larger. And the second item you type here is your natural frequency. So if you hit enter, you get those lines on root locus. Now, in order to see root locus, you need to either type SHG or click on the graph, so you can see root locus. Now, because this is a zoomed version, you don't see as wide as you should see. So what you can do to see a wider area is to use this command access. So type access, open parentheses. Access needs a bracket, a vector, that gives you minimum value of x, maximum value of x, minimum value of y, and maximum value of y. So it defines how wide you want to open the window of the figure. So if you type axis, negative 0.6 is minimum value of x, 0 is maximum x, minus 0.6 and 0.6. So it basically adjusts the figure for you. So you can see better, and you can redraw the root locus. And sgrid. So axis should be before root locus. Now what you can see is if you click on your root locus, so if you click anywhere on the blue area, the root locus area, you can move your black dot around, and you can see that each point is associated with a certain value of gain. Look at this. So when you are on the asterisk, gain is 0. So that's the open loop system. As you move to the left, this is associated with various values of the controller gain. So for example, here we have control gain of almost 1. And that control gain value, you can see on the plot that the pole of the closed loop is located at -2, which is associated with damping ratio of 1. Our pole never leaves the real axis, so damping ratio will always be 1. And it is also associated with natural frequency of 2. Remember, we need a natural frequency of at least 0.36. So at 2, we have already achieved that natural frequency. So we are already to the left of the natural frequency that is desired for us. So any gain, basically any non-zero gain, would satisfy the requirement for overshoot. There would be no overshoot because we never leave the real axis. So the damping ratio is a perfect 1. And even our open loop pole is to the left of that semicircle. So even at open loop, we have the reach time that we want. Now, the next requirement is about the steady state error. The next requirement is about the steady state error. And if you recall last time, we also calculated the steady state error by looking at the transfer function between E and R. Let me remind you of that because this is a very important transfer function. One of the requirements for the design was that the steady state error, when everything settles, when the system stops moving, we want the steady state error to be less than 2%. Now, we want the actual R value. R value is 10, which means Y needs to reach to as close as possible to 10, and 2% of 10 is the window of error that we could tolerate. Now, in order to get to a steady state error, we need to get to error itself, which is a time varying variable. So error changes. So what we did last time was to find this, this transfer function, which is the transfer function between input R and output error. So we applied the same concept. We said between E and R sits no dynamics. No block sits between E and R. So the numerator of the overall transfer function there is 1. But the denominator is always 1 plus content of the loop. So 1 plus k times this. So in steady state, we can calculate value of E through final value theorem. So the theorem says E steady state is S times E of S when S goes to 0. And E of S comes from this transfer function. And we need to specify R. So R is 10 over S because this is a step function with amplitude of 10. So if it was unit step, it would become 1 over S in Laplace domain. But since the value is 10, the Laplace transform of R of S is 10 over S. So R of S is 10 over S. So we multiply that by the transfer function. And these two, when they get multiplied by each other, you get from it E of S. So S times E of S when S goes to 0, we find the steady state value of error to be 10 times 1 over 1 plus k over B. B has a known value. B is 50. So this then therefore becomes 10 times 1 plus k divided by 50. So if you want this to be not more than 2%, 0.02 times 10, then you can calculate the actual value of k that would deliver that steady state response. So please take a second and calculate k, and then we will simulate our system with that value of k to see if we actually achieve the steady state error that we want. So what is the value of k? So if you simplify this, it becomes, you can divide both sides of this by 10 and then divide it by 0.02. So what you can get is 1 plus k divided by 50 is equal to 1 over 0.02, which is 50. So this is 50. So k divided by 50 is 49. So what is the value of k then? It's 50 times 49, which is 2,450. So the expectation is if we have a controller gain as at least at 2450, the steady state error would be less than 2%. And by the way, this is a significantly large gain. Remember, in order to deliver on the transient characteristics of the response, k simply needed to be non-zero. So any number larger than 0 did deliver the transient portion of the response. But in order to achieve the desired error, we have to have a very large error. And let me take a second and say to you that k is not free. It's not simply a number that you dial up. K has a significance here. Basically, it defines how much input you need to put into your system. And input is not free. Now, just go back to the example of the car. When you want your controller gain to be a large number, look at this block diagram. So when you want, in response to a small error in velocity, to put a lot of force into your car, that simply is not a number. That means a larger engine. So you can't simply apply a larger force just by dialing a number up. In physical system, it has a meaning. So generally speaking, you don't want to have a large value of controller gain because it costs you. It costs you to produce that level of force in order to achieve the desired steady state. Now that tells you that the proportional controller inherently has a limitation. Let me bring this general equation, the general calculation that we did for steady state, up one more time. So for a general first order system, we calculated y steady state to be k times a over b times k times a. What are a and b? Let me show you one more time. Where a is the numerator of the open loop transfer function and b was the location, defines the location of the pole. So this calculation that we did last time tells you that y steady state is ka over b over ka. So if you want y steady state to be 1, k has to approach infinity. So it has to be a very, very large number. So 2% requires a k that is more than 2,000. So that is one of the limitations of a proportional controller. So let's take a note of that, so for future, because when we later on will look at other types of control methodology, we want to bring that up. So k is very large. K means more expense, so it costs more. It actually has a physical meaning. So as you want a larger k, you have to spend more money, generally speaking, to get to a larger value of k. So this is a limitation. So this is a limitation of proportional controllers. What is the limitation? For E steady state, to go to 0, essentially your k needs to approach infinity, which again means quite expensive of a controller. So that tells you right away that we need to do better. We need probably a better control logic, which will come later. But let's go ahead and simulate that. So let's go back to MATLAB, please. And so we already have the system in our memory. So it's 1 over 1,000 plus 50. But this is the open loop system. So let's look at the step response of the open loop system. So step response of G. So this is the step response of the open loop system. So if you give it 1 unit of force, if you give your car 1 unit of force, it will get to 0.02 meters per second of speed. Where we want this to be is 10. So we want the output to reach 10 and stay at 10. And the way we are going to do it is by creating a feedback loop. So we are going to create a new system, call it H, which is going to be feedback. So feedback of our K times G. And in the feedback loop, we have simply 1. So in the feedback loop, we don't have a dynamics for the sensor, so this is 1. And we haven't defined what K is going to be yet, so we need to define K. So let's start by a small number for K. Let's say K is 100. So I type K is equal to 100. H is a new transfer function made of feedback of K, G, and 1. So it goes ahead and calculates your closed loop transfer function. Now let's double check and see if this closed loop transfer function 100 over 1,000 s plus 150 is what we have or what we would agree with. So if you look at the closed loop transfer function, the closed loop transfer function that we calculated is K over m times s plus b plus K. So let's calculate it. If K is 100, like what we did, y over r would be 100 over 1,000, which is m times s, plus b is 50, plus K, which is 100. So you get 100 over 1,000 s plus 150. And if you look at MATLAB, that is exactly what MATLAB has calculated. So the command feedback basically calculates for you the closed loop transfer function. So you don't have to apply the golden rule of reducing the transfer functions. Any questions before I go forward? Anything on MATLAB or? Okay, now that you have the transfer function of the closed loop, you can look at the step response. So you can say step, you can type step, and it's step response with an input of 10. So you can say step response of 10 times h, which is the new transfer function, and see how it will behave. So you can see that it reaches close to 7, but not quite where you want it to be. So you want the output of the system to be as close as possible to 10. And by the way, we have calculated K needs to be over 2,000 to get close to that. So let's go ahead and apply that K. So we are going to just hit the up arrow and change the K to 2,450. Was that the number we calculated? What was the number? 2450. Yeah, 2450. So we are going to, with this K, again calculate the closed loop transfer function. So H is feedback of K times G, 1. So the new transfer function is 2450 on the numerator, 1000 S plus 2500. So again, we can look at step response of 10 times H. And you can see now that we get very close to 10. So as we increase K, we get closer and closer to the desired output, to the reference input, but at a very high cost. With this type of controller, it takes a lot of input to get to where we want to be, which is close to 10. Okay, I'll give you a few seconds to play with that. Use different numbers and for your controller gain. and see the difference it makes. So one thing, for example, you can do is you can look at step response of G, the open loop system, well, when it receives an input of 10, and compare it to step response of closed loop on the same plot. So blue here is the open loop, and you can see open loop doesn't even get close to 10. So the benefit that the closed loop offers is that it gives you the steady state response you want, which is for y to match value of r10. And look at the green, and you can see that it is significantly faster than the open loop system. See, the open loop system takes about 20 seconds or maybe more to get to its steady state response, and the closed loop system immediately jumps up because we have displaced the pole towards the left side of the complex plane. That's why you have a much faster response. And if you click on Simulink, I can show you how to build the same thing in Simulink. So go ahead and create a new model. Under continuous, bring a transfer function, and the transfer function has 1050, 1 over 1050. So this is the open loop transfer function. This is the car model where input is force, output is velocity. And you need a controller gain. This is our K. I brought a gain. And we need also a summation sign. So I'll bring a summation sign here. I also need something to introduce my input. I'm going to bring this constant here. So I have now all the blocks I want. So this is my R. And I'm going to double click and change it to 10. That's my R. I'm going to double click on this summation and change the second summation to negative. So it would be a negative feedback. So this gets connected to one side. The output of comparison gets connected to my controller gain K. So I'm going to type it as K, so we can change K without double clicking here again and again. So this gets connected to the system, and this gets connected to, this is the feedback loop. And in order to see how the system behaves, you can bring a scope. So you can look at the actual response of the system. Now, because this is a variable, you need to go to MATLAB and define K to be 2450, for example. And then once you have it, you can go back to Simulink and run the system. And then look at the response. And you can see that the response starts from 0 and gets very close to 10. And you can zoom in to see the actual number. So it gets to 9.8, which is within the neighborhood. So we wanted this to be away by 2%, which is 0.2 in this case, and we have achieved it. And this is no coincidence. We did calculate the value of K that will give you this steady state error. Now let me ask you this question. If K gets larger than what we plugged in, 2450, do you expect the response to get closer to 10 or gets farther away from 10? What would be the effect of increasing K even further beyond 2450? Yeah, if you look at the equation for error steady state, K is in the denominator of error steady state. And error steady state, by the way, is the difference. So let me write this down. So if you look at the block diagram, error is the difference between R and Y. So error steady state, Steady state error is the difference between R and Y steady state. So how far the output of the system is from the desired output or reference input. So in a steady state, when Y stops changing, the difference, we want this to be less than certain percentage, and with that percentage we calculated that value of K. So if K gets larger than the value that we have already calculated, the expectation is that steady state error gets even smaller, which means Y steady state gets even closer to R. So let's go ahead and try that. So if we go from K of 2450 to K of 3000, for example, and rerun the simulation, because now the K value has changed, so you need to recalculate everything, and click on scope, and you can see, yes, we got even closer to 10. So previously it was as 9.8, but it's now slightly higher, so closer to 10. Again, I'll give you a minute or two to play with Simulink, play with MATLAB, and let me know if something doesn't make sense. Yes? I tried, but something went wrong, and Windows needs updating on this machine, and I'm afraid of updating because everything will pause. So if something is not visible, tell me, and I'll either try to blow it up. What needs further magnification?
That whole system, can you blow it up?
Oh yeah, I'll try. Yeah. Better?
Perfect.
Can you see better?
Yep.
Yep. So again, still take your time and work with that system. Our next example is this fourth order system. So far, we have only looked at a first order system where the open loop system has one pole, and so does the closed loop system. The difference between closed loop and open loop was with closing the loop, we were able to displace that pole, to move it around, and therefore create different transient as well as steady state characteristics in response. So we now want to go to a system that has a higher number of poles, so to see a more complex shaped root locus. And for that, I want to, I didn't emphasize this enough, so I want to go back to the rules that apply to all root locus one more time and start from there. So this essentially summarizes all the properties of a root locus. So one of the main properties is that when an open loop system has n poles, the closed loop system will have, with a proportional controller that is, the closed loop system will have as many poles. So if a system, for example, has 4 poles, the closed loop system still has 4 poles, which means the root locus has 4 branches on it. When with one system we had one line, one branch showing how that single pole moved. But if you have 4 poles, there would be 4 lines or 4 shapes showing how those poles will move. Now we discussed the meaning of zeros of transfer functions. A transfer function has a zero when there is a value of s that would make the numerator of the transfer function equal to 0. So one of the very important rules of the roots for root locus is if you have m zeros, m of the branches of root locus will end at zeros of open loop. And I will show you what that means in the context of the example that we just started discussing. So look at this example, please. This example has if you look at the denominator, there are 4 values of s that make the denominator equal to 0. So therefore, this system is a 4th order system. It has 4 poles. How many zeros does the system have? How many values of s will make the numerator of the transfer function go to 0? Just 1. S equals negative 7 is the only 0 of the system. Now, if you look at excuse me, if you look at the root locus, here's the root locus. If you look at the root locus will have 4 branches. And where are these 4 branches? Look at the 4 various colors that we have. We have blue, we have cyan, we have red, and we have light blue. So these are the 4 branches of root locus. So all the branches start from the poles of open loop. So one of them starts from 0 because we have s equals to 0 as one of the poles. The next one starts at s equals negative 5 because the next pole is negative 5. The next one starts at s equals negative 15 because negative 15 is the 3rd pole. And the last one starts at negative 20. So all the branches start at open loop poles. That was rule number 1, or one of the main rules. Now, this system has only 1 0, and that is negative 7. And one of the branches of root locus starts at negative 15, but ends at negative 7. So remember, all of these branches basically show as k starts changing from 0 to infinity, how the poles will move. So for this specific pole that is at negative 15, as you move the pole, that pole, as you increase k rather, that pole starts from negative 15 and gradually goes towards negative 7. So that specific branch. Now, what about the other branches? Because there are not enough zeros for those branches to migrate to, they will simply go to infinity. Because when there is no pole for the transfer function, essentially when there is no other 0 for the transfer function, essentially those zeros are at infinity. So s equals infinity basically makes the, as if s equals infinity makes the numerator of the transfer function equal to 0. Do you remember the concept of dominant poles? Dominant poles? So that concept is very much alive and applicable here. How so? Look at this system. This system has 1, 2, 3, 4 poles. 2 of them are the dominant poles. Can you tell me which 2 are the dominant poles? In other words, would these 2 be the dominant poles, the ones that are closer to the origin, or these 2 that are farther away from the origin? Which ones would be the dominant poles? Yes?
Closer to the origin.
The closer to the origin, those poles are the slower, which means their effect stays around longer. So what I wanted to bring to your attention is, when you're dealing with higher order systems, when it comes to designing controllers for higher order systems, you pay attention very closely to the dominant poles and you try to relocate them to create the desired response, because the effect of non-dominant poles are not as important. Their effect goes away over time very quickly. So let's focus on this example. Again, we want to design a proportional controller so that the overshoot is less than 5% and the rise time is less than 1 second. So I will give you 30 seconds to calculate the required natural frequency and the required damping ratio. Tell me what is the required natural frequency and the required damping ratio for this system. So essentially what we are trying to do is close the system. So if this is h of s, we are creating a negative feedback with a proportional controller. So that's what we are trying to create. So if you plug those numbers, the numbers are, we want the rise time to be 1 second and less. That means that your natural frequency has to be more than 1.8 radians per second. So at least natural frequency has to be 1.8 radians per second. And we want the overshoot to be less than 5%. So if you plug for max MP as 0.05 in that formula, you get to zeta of 0.7 or larger. So zeta of 0.7 and larger will give you an overshoot of 5% or less. So these are the requirements. So the next question is, what value of K will allow you to satisfy these requirements? And I'll give you a minute to use MATLAB and find that value of K that would satisfy these requirements. So go ahead and use MATLAB to create the root locus, and from the root locus, find the value of K that would give you zeta of 0.7 and more, and natural frequency of 1.8 radians per second and more. So let's go ahead and define the transfer function. So this is our transfer function. And to make sure, we can plot pole zero map of this transfer function to make sure we have the poles and zeros where we want them to be. So the open loop transfer function has a pole at 0, another one at -5, another one at -15, and another one at -20 when the circle shows the location of 0. So we have 1, 0 at s equals -1. So we have the open loop transfer function correctly. So the next step is to find root locus of the transfer function. And remember, there are two values that are of importance to us. Zeta of 0.7 and natural frequency of 0.8. So if we can get S grid of 0.7 and 1.8, basically they will draw guiding lines so we know which area of root locus is acceptable to us. Okay, so let's take a closer look at the root locus. The root locus has how many branches? How many branches? It must have 4 branches, equal to the number of poles of open loop. After all, root locus basically tells this story, how the poles would displace as you change value, as you change the controller gain k. So there are 4 branches. Now, the 2 branches that are to the left, the one that starts from negative 20 and the one that starts from negative for some reason, my pole zero map doesn't show on MATLAB side, doesn't show all the poles. Do you see all 4 branches in your root locus? So do you see a figure that looks like this? Oh, I see what the mistake I had is this is 7 and I chose 1. I apologize. So this is at negative 7, and the other one is S times S plus 5, 15, and 20. 5, 15, and 20. It is strange because I do introduce a pole at negative 15, but I don't see it in my pole zero map. So let's try one more time. So I had a typo. I found the typo. Now it should work. Okay, now I have 4 poles. 0, minus 5, minus 7 for zeros, and it's okay here. So let me make sure it is okay here. Yes, so there are 4 branches. And this needs to be 7. I have this typo, so let's correct that. Yes. Okay. So that this is the correct root locus. And now we can add the 0.7 damping ratio and 1.8 natural frequency using the sgrid command. Now, let me bring to your attention that these two poles, the one that starts from negative 20, with increasing K goes further to the left. So it becomes even less dominant. So its effect goes down faster. The other one that is originally at negative 15 stays also to the left of the other two poles. So still it's not a dominant pole. So the point is that these two poles that start from 0 and negative 5 are going to be the dominant poles. Okay, so this is 0.7. This is line of 0.7 for damping ratio. So we need to be to the left of these two lines in order to satisfy the damping ratio requirement. So, and you can see that these two poles are to the left of this anyways. But this semicircle 1.8 defines natural frequency. So we need to be outside and to the left of that. So if you click on the plot, you can see where is the first time that the plot gets outside this area. So K of 0, of course, the pole is at 0, and with K of, so a K of 250 gives a natural frequency of 1.8, so it has to be more than 250. So the next calculation that it does is at 300, and you can see this is already above 1.8. So something around 300 and more is expected to give you the required rise time and the required damping ratio. Now, the fact that no matter what value of K you use, the fact that no matter what value of K you use, the two poles are going to be within this 0.7, at least initially, because if you increase K large enough, eventually this will go outside these two lines. Let's try this point, for example. At this point, when gain is 773, you can see damping ratio is less than 0.7. And as gain increases further, damping ratio further decreases. So at least 300, but not more than, let's see, not more than 500 something. So between 300 and 500, you can satisfy the requirements. So again, take your time and play with root locus. You want to click on a branch and move around and see what values will give you the required response of the system. So we know a K of at least 300 by clicking on the MATLAB figure and moving around will give you the desired response. So let's go ahead and create step response. So let's create the closed loop system. So H is going to be made of feedback of K times G, and with a 1 on the sensor side, on the feedback line. So K, we said at least has to be equal to 300 and should not exceed 500. So K of 300, H feedback of K times G and 1. Then we can look at step response of G and step response. So step response of open loop and closed loop on top of each other on the same plot. So here, the green is the closed loop, blue is the open loop, and again, you can see that closed loop shows the exponential rise. It gets 2 to 1 quickly. So let's go back to the requirement. We wanted the rise time to be about 1 second. So we wanted in about 1 second we get to 90%, from 10% to 90%. So 10% is here. It's 0.25, and 90% is here. So it takes more than that. So we need to further increase the gain, so we have a larger value of natural frequency. So let's go to 400, because root locus showed at least 300, more than 300. So let's go to 400 and look at the response. So with 400, this is the response we get. So now we are roughly at that time. So 10%, from 10% to 90% roughly takes 1 second. But if you want to make the system even faster, you need to further increase K, which will in turn increase natural frequency of the two dominant poles. So with 500, you can see that you get even closer to achieving that 1 second rise time. So now 90% is here, 10% is here. It definitely takes less than 1 second. Now we have a little bit of overshoot. So we wanted overshoot to be less than 5%, so 1.05. So you can see as you increase K, overshoot increases, but also rise time decreases. And the reason should be clear if you look at the root locus. If you look at the root locus, each of these two dominant poles, as you increase K, would start moving away, and eventually they meet here. They are equal at this point, and this is the value of K equals 308. So at up to 308, there is no overshoot, because the damping ratio is perfect 1. After 308, with each of these branches, you start having overshoot. So as you increase K further to 365, for example, damping ratio goes from 1 to 0.92, and overshoot is now roughly 0.03%. Increase it further, overshoot gets to 0.5%, damping ratio goes down, and this trend continues. So that's the benefit and strength of a root locus. It basically gives you an overall picture of what happens to the system as you change the controller gain. And this was an example of a fourth order system. So let's go back to the slide and review what we learned. So let me remind you that this was a fourth order system, which meant the root locus had 4 branches. Each of them started from one of these open loop poles. One started from S of 0, the other one started from S of -5, the third one started at S of -15, and the last one started at -20. One of the branches, which in this time happened to be the third branch, the one that starts from -15, ends at the open loop 0, which is at -7. So that the branch is very defined. It starts from -15 and ends at -7. The other branches simply go asymptotically to infinity. So -20 keeps going to the left as K goes towards infinity. And these two branches initially come together, and then they separate and go off. And we further, based on the performance that we needed to have, we found the area that is acceptable on root locus. We decided that we want a certain natural frequency and larger to achieve the speed of response, the rise time that we wanted, and an area of damping ratio and larger value to achieve the percentage overshoot and stay below that. And in root locus, we can actually bring those area and highlight them so we know graphically where the two poles can be located. So that example serves the purpose of bringing to your attention how the root locus works. Okay, so far we've been focusing on starting from a transfer function and staying at transfer function. This is our next example. So this is a second order system where we have a state space model. So A matrix is 0, 1, 0, -3. B matrix is -1 and 4. And C matrix is 1 and 0. So I want you, as the first step, to find the transfer function. The formula is on the board. So go ahead and apply this formula and find the transfer function of the system between input R and output Y for the open loop, and then we will find the closed loop together. So go ahead and calculate the open loop transfer function. And before that, please calculate the eigenvalues of matrix A also. As you recall, in order to calculate the eigenvalues, we need to set up the determinant of lambda I minus A and set it equal to 0. So lambda I is simply a matrix made of lambda, 0, 0, lambda. Identity matrix is 1, 0, 0, 1, and when you multiply the identity matrix by lambda, it becomes lambda, 0, 0, lambda. Now, if you create lambda I minus A, it means each of the elements of lambda I gets subtracted by the corresponding element in A. So lambda gets subtracted by 0. So lambda minus 0. 0 minus 1. 0 minus 0. And lambda minus 3. So this is lambda I minus A, which is therefore lambda minus 1, 0, lambda plus 3. Now if you set up the determinant of lambda I minus A, so determinant of lambda I minus A is going to be lambda times lambda plus 3 minus 0, which is 0. So that's the determinant. If you set this equal to 0, there are two values of lambda that will make this equal to 0. Lambda 1 is 0, and lambda 2 is negative 3. So that tells you that this system has two eigenvalues. Two eigenvalues for matrix A. One of them is located at 0, the other one at negative 3. Now, could you pause for a second and answer this question? If you find the transfer function for this system, can you tell me what the poles of the transfer function are going to be?
0 and negative 3.
The poles of transfer function are identical to eigenvalues of matrix A. Now, let's go ahead and find the transfer function through this formula. C times Si minus A inverse times B plus D. So we need to go ahead and form Si minus A. Now, we already found lambda I minus A, so Si minus A is simply taking lambda and substitute it with S. So it becomes S negative 1, 0, S plus 3. That's Si minus A. Now, what we need is Si minus A inverse. So inverse of a 2 by 2 matrix is you move the diagonal terms, so this becomes S plus 3, and change the sign of the off diagonal term. And you divide by the determinant. The determinant we already found is S times S plus 3. So this is Si minus A inverse. We can further simplify that. So Si minus A inverse, if you divide through by the determinant, S plus 3 divided by S times S plus 3 becomes 1 over S. This is 1 over S times S plus 3. This is 0, and this is 1 over s plus 3. We didn't have to take this step, but we might as well. Okay, so we have its Si minus A inverse in one 2 by 2 matrix. The next step is to pre-multiply it by C, where C is 1, 0. So if you take C and pre-multiply Si minus A inverse by it, C is 1, 0. So it is a 1 by 2 matrix that is being multiplied by a 2 by 2 matrix. So the result is a 1 by 2 matrix. So the first, so 1 gets multiplied by 1 over S. So this is what survives from the first column. And from the second column, you will have 1 over S times S plus 3. Remembering that C, as we have it up here, is 1, 0. So 1, 0 gets multiplied by the first column. So the first element would survive. And when it gets multiplied by the second column, again, the first element survives. So that's C times Si minus A inverse. The next step is to post-multiply this by B. So we need to take C times Si minus A inverse and post-multiply it by B. B is a 2 by 1 matrix made of -1 and 4. So this is going to be 1 over S, 1 over S times S plus 3. This is going to be multiplied by -1 and 4. So the dimension, 1 by 2 here, 1 row, 2 columns. This is 2 by 1. So the result is 1 by 1. So the result is a scalar. So this becomes, so -1 over S plus 4 divided by S times S plus 3. So this becomes equal to, so S times S plus 3 will become the common denominator. So S times S plus 3. So here we have minus S plus 3 plus 4. So this becomes 1 minus S. So MATLAB has a command that does the calculation that we just did. So so if you give the four matrices A, B, C, and D to a command called a state space to transfer function, it gives you the polynomial for numerator and polynomial for denominator. I wanted to double check our work. So the polynomial that we found for the numerator, power 1 of s is -1 and power 0 of s is +1. So that checks with what MATLAB found for us. And in the denominator, power 2 of s has a coefficient of 1, power 1 of s has coefficient of 3, and power 0 of s has coefficient of 0. So it's s squared plus 3s plus 0s. So I double checked our work with this command in MATLAB. So the command in MATLAB is called state space to transfer function, SS number 2 to TF. And for that, you need to give it matrix A, B, C, and D, and tell it which of the, if you have multiple inputs, which one of the inputs you want to use as your input. Here we have only one, so by default, this would be a number 1. So you would put 1. And here, this is going to be equal to numerator, comma, denominator. Num, com, den equals to this. So by that, you can get the polynomial for the numerator and polynomial for the denominator, which we did for this example using MATLAB. Okay, so that was the very first part of, or the second part. Now we want to go ahead and calculate the poles of the transfer function. And still, this is the open loop transfer function. So if you look at the transfer function, can you immediately see the poles of the transfer function? What are the two poles? The two poles, so the poles, S pole 1 is 0, and S pole 2 is -3, which are identical to the two eigenvalues of matrix A. Now, what is also interesting is value of 0. So we have 1, 0, and that 0 is located at +1. So S equals 1 will make the numerator of this transfer function go to 0. So can you tell me immediately how many branches would the root locus have? Root locus will have 2 branches because the system has 2 poles, and you know that one of the branches would end up at the 0 of the system. One of the 2 branches will end up at the 0 of the system. So let's take a quick look at the root locus. So go here. So G would be 1 minus S rather. 1 minus S divided by S times S plus 3. So we need to define S and then define so if you look at R locus of G, this would be the root locus. So the 2 branches start from 0 and -3. And we'll look at how we get to this figure in a second. But I want you to get an initial image. So let's go back to our example. So we found the 2 poles. Now we want to go ahead and create a proportional controller. So what does it mean to proportional control? As before, this means we are going to close the loop. So this system, we're just going to just call it system, will have an output that will take and compare to the reference input through a plus minus sign, and we'll send the result, which is the error, to a controller, to a proportional controller, which in turn will define the input. This is the controller we're trying to make. So the question is, where are the two poles of the closed loop system is now located? So the first thing to do is in transfer function domain to find y over r. As you know, it is going to be k times the transfer function of the system, 1 plus k times transfer function of the system. So the transfer function is, as we have found, 1 minus s over s times s plus 3. Both in the numerator as well as the denominator will have that. So s times s plus 3 becomes the common denominator, which helps us simplify this transfer function to k times 1 minus s in the numerator. And in the denominator, we'll have s times s plus 3 plus k times 1 minus s. Okay, so where are the two poles located? So we need to find the polynomial for the denominator. So we are going to only focus on the denominator. So let's multiply this out. So we get s squared plus 3s plus k minus s. So this can be further simplified to s squared plus 2s plus k. And we need to set that equal to 0 in order to find the poles of the closed loop system. So we are now trying to find the location of poles of the closed loop system. So the two values, s, p, 1 and 2 are going to be, this is a second order polynomial. A is 1, b is 2, and c is equal to k. So minus b, so which is minus 2, plus minus b squared, which is 4, minus 4ac, which is minus 4k, divided by 2a, which in this case becomes 2. Any questions, guys? Yes.
When you multiply that all out, should it be minus ks? Because you distribute the k.
Yes, absolutely. Yeah. This should be ks.
Yeah.
Yep. Thank you. So this is ks. So this becomes ks right here. Okay. So this becomes k times s. So it is, okay, it's easier to rewrite it. So 3s, then we have plus k minus ks. So let's simplify that. So this becomes s squared plus 3 minus k times s plus k equals 0. Is it correct? Thanks for the correction. So the two values that will make the denominator of the closed loop system go to 0 are the two poles of the closed loop. Again, the same concept. So minus b, which is minus 3 minus k, plus minus b squared, which would be now 3 minus k squared, minus 4ac, which is minus 4k, divided by 2a, so divided by 2. So minus b minus 3 minus k plus minus b squared minus 4ac divided by 2. Okay, so we can make another little table here. So K values would be on the top, and values of SP1 and 2 at the bottom. So when K is 0, what are the two values of the poles of the closed loop system? So set K equal to 0, so you have minus 3 left from the first parenthesis, minus 3 plus minus square root of 3 squared, which is 3. So you have minus 3 plus 3 minus 3 divided by 2. So one of them would be, so minus 3 plus 3 divided by 2 will give you 0. And minus 3 minus 3 divided by 2 gives you minus 3. So you have two poles, 0 and minus 3. And that's expected. So when K is 0, you get the poles that are exactly the open loop poles. So let's go ahead and calculate K of 1. Maybe you need to use your calculator here to quickly calculate these. So on the monitor in the middle, I have brought the root locus. So we know at K equals 1, the two branches, the two poles actually meet each other. And the reason is that the square root that differentiate the two. So see that plus minus differentiate the two poles. So at K equals 1, you have 3 minus 1, which is 2 squared 4, minus 4, it is equal to 0. So at K exactly equal to 1, that square root goes to 0. So you have 3 minus 1, which is 2 minus 2 divided by 2. So the two poles are both located at negative 1. So negative 1 and negative 1. So the two poles are on top of each other. Can you see that? So the two poles come together, and at exactly K equal to 1, they meet. And if you look at the root locus, the two poles are located. It gives you the value of gain. It gives you the location of poles. It gives you the damping ratio. It gives you the overshoot. And it also gives you the natural frequency. Natural frequency is the distance to the origin. When they meet at negative 1, obviously the distance is 1. So 1 radians per second. Now, if you keep increasing the gain, one of the branches will go up and the other branches will go down. So this plus minus will create a different value both for the real part as well as for the imaginary part. That's why they move on a semicircle. Now at K exactly equal to so it's between 2.9. I think it's equal to 3. So at K exactly equal to 3, the real part goes to 0. Now look at the equation we have. So if K is exactly equal to 3, this portion, the first parenthesis, goes to 0, which is the real part. So this goes to 0. This portion also goes to 0. So you have square root of minus 12 divided by 2. So you have plus and minus j square root of 12 divided by 2. So the two poles are purely imaginary, which means what? Which means damping ratio is exactly equal to? Damping ratio is what when you are on imaginary axis? It's the other extreme. It's exactly equal to 0. Remember, the angle with the imaginary axis, the sine of that angle is equal to damping ratio. So when that angle is 0, its sine is 0. So damping ratio is exactly equal to 0. So when K is exactly equals 3, you have 0 damping ratio. 0 damping ratio, which means you have 100% overshoot. So this simply oscillates. The response will simply oscillate and will not decay. And natural frequency is 1.7 radians per second. Do you remember that this system had a zero at +1? This system has a 0 at +1. There is value of s equals 1 that makes the numerator of the transfer function go to 0. So it has a 0 at +1. That's why you can see one of the branches, when it meets again here, eventually goes to 1, and the other branch goes to infinity. Now, this area of root locus, this area to the right of imaginary axis is problematic, because as soon as one of the poles, in this case both poles, travel to the right of the imaginary axis, you're now dealing with an unstable system. An unstable system, which means you give it a limited input, but the output grows significantly without bounds. And we are going to try that. We are going to look at the feedback response of the system. So let's write this down. So here at 1, zeta was equals what was equal 1. At 3, zeta was 0. And between 1 and 3, zeta was between 1 and 0. So we're dealing with an underdamped system. Now, if we are going above 3, the system becomes unstable. So if you go above 3, the system becomes unstable. So let's go ahead and create a feedback system. So H is equal to, so for now let's assume K is 1, and we are going to change it. It's going to be feedback of K times G with feedback of 1. Step response of G and H both. Now let's pause for a second and look at our open loop system one more time. Open loop system without any control. Here's the transfer function of the open loop system. The open loop system has a pole at 0 and a pole at -3. A pole at 0 and a pole at -3, and it has a 0 at -1. Now, when a system has a 0 at exactly 0, this system is not unstable. It's not an unstable system, but it acts like an integrator. It acts like a tank of fluid that has no opening. So what you put in it gets accumulated. So if you give it a constant input, its output is going to be constantly increasing. And that is exactly what you see in blue. Blue is the open loop. So if you give it a constant input, its output is going to constantly increase because of the pole at 0. That's the reason. Now when you close the loop, your pole is no longer located at 0. So you have displaced the pole. It's no longer at 0. So that's good news. So you no longer have an integrator. Now at K of 1, you have a critically damped system. Damping ratio is 1. So if you wait long enough, you can see that this eventually will settle. So the green shows that the system essentially settles at a specific value. Now let's try a number that is larger than 1. You know, after 1, look here. After 1, you start having some oscillation. So you have an underdamped system. So let's try K of 2. See, with K of 2, you see a clear oscillation, clear overshoot, but system is eventually settled at Y steady state of 1. The open loop system still behaves the way it used to behave. We haven't done anything. I just put the open loop system for comparison. So open loop system is still the same, but for closed loop with K of 2, you have that created that response. Now let's increase K. We know at 3 we are going to be damping ratio of 0. So let's try that. Let's try K of 3. See, damping ratio is 0 now. So the system keeps oscillating without any decay. Now, as soon as you go beyond 3, the 2 poles will go to the right-hand side of the imaginary axis, and you will have an unstable system. So let's just try 3.5. See? The system's response starts growing. It oscillates still because it is a pair of complex conjugate, but because now it has a real positive part, its amplitude basically grows. And if you look at the root locus, guys, this semicircle eventually meets again. What is this value? This is exactly equals 9. So at K of 9, the 2 poles become real again. So if you set your gain at 9, the system is still unstable, but you will no longer see any oscillation because the imaginary part of the 2 poles go away. So let's try that case as well. So let's try K of 9. And you can see there is no oscillation, but the system is still unstable. So the amplitude of response basically grows without bound. So we are dealing with an unstable system. Okay, so what we avoided here was to try to deal with state space model. So we took our state space model into transfer function and then forgot that we had a state space model, and we did everything in the transfer function domain. The question is, can we do it in transfer function? Can we not convert this to I'm sorry, let me repeat. Can we stay in state space model and not transfer to a transfer function model and still create a closed loop system in that domain? The answer is yes. So we are going to spend some time and look at that case. So the question is, so this is the root locus again. The question is, what if we want to do this at the transfer function? So let's revisit what we are doing. So we have our system. In this case, x dot is equal to ax plus bu, y is cx plus du. This system generates y in response to an input u. We want to create a closed loop system with a proportional controller k that will calculate u based on the error that is the difference between r and y. Okay? Now, what is r, guys? What is r? Because reference input. Is it 1, 2, 15, negative 29? What is r? What should r be? The answer is r can be anything you want. Basically, you signal what you want the system to do. Can you see that? Basically, you're saying what I want y to do, what I want the output of the system to become. Okay? So r can be any number or actually a time function. You can say r changes with time. So I want my system to follow a time-changing trajectory. And that's possible too. So r can be anything including r of 0. If we choose R to be 0, basically we are saying we want this output of the system to go from whatever initial condition it has to 0 and stay at 0. Okay? Why do we choose R of 0? Because it makes the analysis easier for us to do. So let's go ahead and see what U would be. What is U? U is multiplication of K and E. So U is K times E. But what is E? E is the difference between R and Y. And if R is 0, E simply becomes minus Y. So it becomes minus K times Y. So the input to the system simply becomes minus K times Y. Can you see that? If R is 0. So how is this helpful? It is helpful in this sense that we have, let's rewrite our state space model. We have x dot as ax plus bu, right? So if you substitute for u as, what is u? U is minus k times y. And what is y? Do we know what y is? Look at the second part of the state space model. Y is cx plus du, and we know d is in majority of cases equal to 0. So we can write y as cx. So let's rewrite this portion of the dynamics. So we have ax plus b times minus k times c times x. So x gets repeated for both terms, so I can factor it out. So I can write this as a minus b times k times 6 times c rather times x. So this is x dot. Now if you compare this to the original state space model, this is our new A. So we are going to give this a name. We are going to call this A of closed loop times x dot. So this is the A matrix of the closed loop system. So the expectation is that the eigenvalues of the A of closed loop would be the same as poles of the closed loop transfer function. And we are going to test this on the example that we solved. So let's add a page here. So let's go ahead and calculate A of closed loop for the example that we are solving. What is A for us? So A is 0, 1, 0, minus 3. So we are going to create, so A is 0, 1, 0, minus 3. And what is B? B is minus 1 and 4. So B is minus 1 and 4. Could you not print here, please? And C is 1, 0. So we have A, B, and C. So let's go ahead and calculate A of closed loop. A, thank you, minus B times K times C. So B is 2 by 1, and C is 1 by 2. So if you multiply a 2 by 1 by 1 by 2, it becomes 2 by 2. So let me repeat. B is 2 by 1, and C is 1 by 2. And K is a scalar. K is the controller gain. So if you multiply a 2 by 1 by 1 by 2, it becomes 2 by 2. So you can subtract this from a 2 by 2 matrix. So let's go ahead and calculate B times C first. So B times C is going to be minus 1, 4 times 1, 0. So row 1, column 1, minus 1. Row 1, column 2, 0. Row 2, column 1, 4. Row 2, column 2, 0. So this is B times C. Now let's go ahead and calculate B times C times K, which is our controller gain. So it would be minus K, 0, 4K, 0. And now let's subtract A from B times K times C. Because K is a number, you can just move it around anywhere you want. Okay, so I need to subtract the corresponding members from each of the members. So it's 0 minus minus K, so it would be plus K here. 1 minus 0, so it's 1. 0 minus 4K, so it's minus 4K. And the last one is minus 3 minus 0, so it's minus 3. Okay, so this is what? What is this matrix? What is this matrix, everybody? This is A of closed loop. So it's A of closed loop. So let's go ahead and calculate the eigenvalues. So lambda I minus A closed loop will give us the eigenvalues for A closed loop. So lambda I, is lambda 0, 0, lambda minus A closed loop, which is K1 minus 4K minus 3. So this would be determinant of lambda minus K minus 1, 0 minus minus 4K, so it's plus 4K, and lambda plus 3. So that's the determinant. So let's carry out this. So it becomes lambda minus K times lambda plus 3 minus minus 4K, which is plus 4K. So it becomes lambda squared plus 3 minus K times lambda plus 4K equals 0. So if you set that equal to 0, you find the eigenvalues of the closed loop transfer function. Have you seen that polynomial elsewhere? So what polynomial are we talking about? The polynomial that we found is lambda squared plus 3 minus k lambda plus 4k. Let's call this equation 2. And let's compare this equation 2 to this equation. Equation 1 that we found through the transfer function route. So what did we do? We found the transfer function of the closed loop, and we found, we set the denominator of that transfer function equal to 0, and the polynomial that we found was s squared plus 3 minus ks plus k. So there is a difference here. Why? Where did we make a mistake? So these should be identical unless I have made a mistake. So let me see if I can trace back quickly to where I made the mistake. So lambda squared minus 3k. Okay, so what I missed is minus 3k that comes from this multiplication. So I apologize. Let me include it and then. So I wanted to write this quickly, so I missed one term. So this has a minus 3k that comes from the multiplication of minus k and 3 plus 4k. And if you simplify that, you get exactly the same equation. So it's lambda squared plus 3 minus k lambda plus k equals 0. So this is equation 2, which is now identical to equation 1 that we got from the transfer function route. So if I want to summarize, I need to tell you just quickly that if you want to stay in the state space route, what you need to do is to create a closed loop A matrix, which for the proportional controller we showed, and it's general, it's not specific to this system, that A closed loop is A minus B times K times C, where B and C are parts of the state space model, and K is the gain, is the controller gain. So there would be a quiz coming after this. The pattern is every 2 classes we'll have a quiz. So this is the second class in the control section. So expect a quiz. I'll send an email as soon as it's released, or I'll give you more details on it. All right, thank you.